So at this point, we have defined a new function, our Hamiltonian, which is a function of the position coordinates, the momentum, and the time. And this has replaced our Lagrangian, which was a function of the position and the velocity in the time. And you could really start to ask, okay, what have we gained by introducing a Hamiltonian as opposed to a Lagrangian? So on the technical side, the use of the Lagrangian, we have n second order differential equations, and we have to provide initial conditions to solve this. With the Hamiltonian, we have 2n first order equations. So there's still the same number of initial conditions that have to be applied, because for the second order equation, we usually will give an initial position and initial velocity. For these 2n first order equations, we'll have to give a position and a momentum. We have that our rate of change of the momentum is a derivative of the Hamiltonian with respect to a position. So if this quantity vanishes, we instantly have a constant of motion. So if this is equal to 0, then P alpha is a constant. Whereas when we derived our constants in the Lagrangian formalism, we had to look for these cyclic coordinates, and it wasn't as straightforward as an application as what we have with the Hamiltonian. The real advantage isn't so much on the technical side, although many mathematicians would say that this is much easier to solve than this in general. But for us, the real advantage of the Hamiltonian formalism is in the conceptual part of it. Here we're looking at positions and velocities of particles, of mass units, of bodies. Here we have positions and momenta. And for most mechanical systems where you're looking at an individual body, whether you decide that you want to deal with a velocity or deal with a momentum, maybe it's not a great conceptual change. But consider if you're examining something to do with a wave. Here, the waves are much easier handled with a Hamiltonian formalism, because you can speak about the momentum in a wave as opposed to the velocity of a particular particle that makes up a wave. So if we think about, for example, a wave on a string, I can have a component of the momentum in the longitudinal direction, even though the individual particles that make up that string would have no component of velocity in that direction. So a wave that is purely transverse in its amplitude, the particles move in a vertical direction, but yet the wave has a horizontal component of momentum. That's natural to apply in a Hamiltonian framework because our momentum is not a simple time derivative of a position, unlike this velocity. So in the Lagrangian framework, it's somewhat more difficult conceptually to see how we can apply things to waves. It can be done, but the Hamiltonian formalism is just much more natural for doing wave mechanics. This is why the Hamiltonian is used in quantum mechanics, because it's all about its wave mechanics. So it's a much better framework to do your normal quantum mechanics with the Hamiltonian system.